It's also a pleasure to be here, first time in India. Happy to present, be introduced by a professor that was well known when I studied in Maryland. Even though I was in the fire protection department, we also took classes in mechanical, so I think I walk by his office very often. So it's a pleasure and honor to be here. I'm going to talk about fire behavior underneath PV panels on roofs. And as part of an introduction to that, there's a massive increase in the use of PV modules for solar panel or for energy gathering. Very exponential. You can see here, for example, this picture is taken from Google Earth, actually. And you can see that here's the picture from maybe 5 years ago, and then the same place, all of these solar panels are now being put on roofs of warehouses and buildings for goals of maybe a zero energy type of building or for in-house production of this. With this, there's also been an enormous increase in fire incidents. Here in Italy, more than close to 1,000 incidents in some year in just one country, and in Germany in 2013 they had 210 fire incidents, and the numbers are similar all over the world. So there is an increasing problem, and we wanted to understand this. And part of this work comes from the fact that companies like IKEA, Walmart, they have very big warehouses, and they don't, they want to have PV modules on their roofs, but they don't want to have fires. It's bad for public image, it's bad for business, but also it's bad for the whole, thought of having increased energy efficiency. If you have a fire and the whole system breaks down, the investment is failed. There's different approaches to it. So if you think of this type of bow tie diagram, so you have the probability, so you can work on decreasing the probability of an event starting. Well, so obviously you can take away, things that start a fire, you can ensure safety to nearby buildings to contain it, or restrict access to roof construction. The other aspect of a risk is the consequence. So you can try to choose adequate materials, design of the roof, or removal of combustible material to decrease these. Overall, so this is the probability and consequence. The product of those is the risk. In our case, what we look at is basically a roof construction should not be designed for if, but when. Because there are so many ignition events, and this is the same for fires in the built environment in general, that there will at some point be an ignition, so we need, whether it's purposeful or an accident, so we want to decrease the consequences when we have a fire. So we basically set the probability to 1. We say we have ignition. We don't study, we don't focus our study on the electrical malfunction and so on, because the statistics also show with all these fires that even though people try to prevent it this way, they will find new ways for electrical malfunctions and other things to happen. So ignition will happen. So we want to look at the fire dynamics of the system, and this is important to emphasize that we look at the system. We don't look at just the panel itself. The PV modules themselves may have just 10% combustible material, so they don't burn so much, but what we're interested in is how they interact with the system they're on, so hence they're on a roof. There is a substrate below them that will have flammable material. So we look at here, intrudes the fire below this system. And then we want to see how can we mitigate or look at these systems. the consequences. So the research is based on an ongoing PhD project and a number of master's students' theses. And I will go through sort of three aspects of this that we've done, various scales and various approaches to look at this system. So we started very basically just to look at what is the influence of the panel itself. So we created a system here where we have heat flux gauges and a gas burner. And we just measure, when we just use the burner and no panel, we measure what kind of heat fluxes do we have in the vicinity. Because the original state before you had a PV panel, that was that maybe you had a fire, and without the PV panel, it wouldn't spread so much. So we put in a PV panel above this burner here, you can see in the lab, and the heat flux gauges. And then with this, kind of obvious, we see that we have an increased heat flux back because of re-radiation. Somewhat counterintuitively, maybe you think that where it's lower, you would have a higher heat flux, but the flame leaning over and goes here due to buoyancy effects. So you have a higher heat flux actually in this region for the spread. And importantly here was to point out also that a lot of the substrates that people use as roofing materials, some plastic membranes, have what's called a critical heat flux, which is the heat flux, kilowatts per meter squared, that they need for self-sustained burning. So even a small burner here under the panel would lead to a self-sustained burning, whereas if you look at before, we would not really have a spread. If you just had an initial fire here, it will not spread because the membrane itself would have too much energy absorbed by trying to heat it, trying to break down the material. But with a PV panel in place, you could have a fire spread. So this already was sort of a small study to show why they saw more fires and more spread of fires in the event of introduction of PV modules. So basically what we see, here illustrated a fire by just a small crib. This is also, we've used a crib instead of electric malfunctions, just to use a reproducible type of fires to start it. Some people may say, oh, there's no crib there, you should use the electrical malfunction. But again, the statistics of all the fires show that any of the electrical malfunctions actually are big enough to start a fire that can propagate. So we're not so interested in what the initiating size is. We want to look at what happens after you have an initiating size that's big enough. We don't make it massive, we just make it sort of big enough that this fire actually would again not spread on just the membrane or not the roof by itself. So we have ignition, you have the heating of the materials, you have this membrane maybe melting, starting almost to boil. The pyrolysis, this starts to burn, and you have a feedback cycle, and you have a self-sustained flame spread. So it was clear from this study that PV installation can stimulate fire spread, and the possibility of the ignition and increased fire load is not the only risk, so we need to look at the system. So some of the things we wanted to do was, limitations of this is obviously small. We wanted to do some more larger scale and with a realistic roof construction and several panels. So the student built a setup. This is from the one side you can see the panels at an angle and the mounting and the roofing construction. It is some different specs here, but also the details. To look here, there's a roofing membrane, and then there's here an insulating type of material, and here it's EPS. So one of the reasons that we do this with EPS, some people say, oh, well, this is highly flammable. Why do you put this on? Well, this is the quite classic roof construction on warehouses, because they have very lightweight truss systems that need a cheap and lightweight insulation, and then normally it was just a membrane on top of that. Because before the fire, before PV panels were introduced, there were no fire risk. So they weren't so concerned about having a very flammable material and just a thin membrane. So now, when they introduce these panels, they want, organizations want to have a mitigation layer, maybe some, and in our case, we do either a polyisocyanate, like a pier, or a mineral wool. These are the two type of main insulation materials that are in place for this. So we built it up, and then of course took a lot of measure of closing on the edge, so we don't just have a spread around the corner and ignite this membrane. So this was existing, and then we put the mitigation layer and vertical protection. The way it looks from the top was we have here 6 panels. We started this place with a relatively small wood crib. Again, a wood crib that if you just put it on the roof, it would not create a fire spread beyond maybe 5-10 centimeters around it. And all of these dimensions is about 6 meters by, we have 2 different sets, but 4.8 meters by 6 meters. So a segment of a roof. And we did 4 experiments here. The 2 small, they were not as, they were not 4.8, but about 3 meters, I think. And then some larger, again, with pier and mineral wool. So this is what it looks like in the field. It was a bit too big to have in the lab. So we do this, and different measurements, thermocouples. We instrumented heavily inside the insulation, because we're also obviously interested in thermal penetration into the mitigation layer, not just across the roof. So this again, what it looks like. Here's one waiting to be burned, and one we had here. And so this is the narrower one. You can see this one is a bit wider, but this one is a picture from a narrower one. And in all cases, all of the fire spread throughout all of the panels, and it also made them all collapse and be damaged. So here's look. But what you can see is that, again, even the fire being relatively large, here you can see compared to the material, it did not spread out to the membrane. So it's clearly that the PV modules, the fire dynamics that they introduce, creates this flame feedback and is enhancing the fire spread. And this has been observed many places also in warehouses where they've had fires, that it spreads to where you have the panels, but then stops. So again, it's the heat feedback from them that creates this situation. If you look at the extent of the fire spread, here's a map of that, and you see even with some wind, people always ask, what's the effect of wind on your fire? When you have journal papers, the critical reviewer said, oh, you didn't consider wind, why didn't you consider wind load? Wind will change it. It's another factor. You can always introduce a larger factor, but in our case, we can even say that even if the wind is going in one favorable direction, it didn't lead to a massive different spread out of this. And this is, again, these are for two different type of insulation materials. If you look, this was when we took the panels away, so the top, the roofing membrane, it's been quite damaged. And more importantly, if we look under the pier insulation, the students and the workers peeled off, this one we extinguished so that it wouldn't burn out. But what we can see was that in the pier, which is a combustible material, a good insulator, but a combustible material, we have traces of combustion happening under or underneath the insulation material. So the fire actually penetrated what was supposed to be the mitigation layer. On the other hand, this is top of the mineral wool, and here the EPS had melted, but there's no combustion. So maybe more of it had melted, but it had not taken part in the fire. So this one was actually just let to burn. So because it was hot and there's thermal penetration, it melted, but it didn't combust. The other one was extinguished. So summary from these experiments was that the PV array facilitates the spread of fire. The fire propagates outside the domain of the wood crib, and the fire does almost not spread outside of the array of this. So the things that we wanted to look at more in detail is then, are there things we can do to then reduce this spread? Because now we see there is a spread associated with it. Are there any things we can do to mitigate it through, cheap solution? Some people may say, oh, well, we can put, sprinklers or some active systems, but this would be extremely expensive and will probably prevent people from trying to install this in the first place. So we need to look for some other solution. So again, we looked at some, go back to the lab and do some more smaller experiments where we can do more parametric studies. It does have a certain cost to build larger experiments. So again, and in the lab we can instrument more heavily, thermocouples, heat flux gauges, camera, scale. This is a top view. And we do an ignition from one end and look at the spread across this. And if you turn it, we also put it on a laboratory jack so that we can play with the height above, the separation distance between the substrate and the panel. And in some cases, we also didn't use a PV panel. We just used a plate, a dark plate, which was a substitute for it. And as you'll see from the results, they are similar. So it's warranted that we can use a plate, not necessarily a panel, because the panel, again, has very little combustible mass. It's more a fire dynamics effect of it. So, what you look at here is, here's no panel, and we have a PMMA plate as a substrate. And we have here is 20 centimeters, and here is 17 centimeters, the separation distance. And if we look at the three videos, you can see that it's a clear change, dramatic change based on the presence of the panel, and also with just a 3 centimeter difference, you have from being just a sort of local fire, you now get a massive non-local fire. So what this shows here again, in these cases for smaller gaps, no panel and larger gaps, you have sort of a linear time distance relationship, whereas for a smaller gap, sort of a critical gap, you get an acceleration into a flame spread that is up to 20 times as fast as with no panel. This is also again reflected in the heat flux. If you look at here's the heat flux measured. If we have a free burning, it's practically none. And then once we reach a certain, this is larger than the critical gap, but then once we reach smaller than the critical gap, we have this takeoff in the radiated heat flux. And again, just to show that the actual PV panels versus just a surrogate panel yield very similar results. So again, and you can see here some damages to this, and actually sometimes the benefit of not using the panel was that then they interrupted the results somewhat with breaking glass and things that were interfering with the analytics that we're trying to do, and not really adding any understanding per se. So in conclusion, overall is that what we're aiming at now is that you can have possibly a critical gap distance, and maybe installation guides can put this in, and just by a small geometric change you can actually have a passive fire protection cheap solution of doing this. It's not said that it's necessarily going to be done, because if you have too high of a distance above, there's wind load and lift that can be created, and a problem associated also with aesthetics and practical issues. But this is something that is truly worthwhile looking into. So yeah, so basically what I said. But it's interesting that just by small geometric changes we can actually probably mitigate a lot of the problem. So just wanted to say the team, well, that's me, but most of the slides and the work is done by my PhD student Jens Christensen. Well, he's a student at the University of Edinburgh, but because of personal health reasons, he's currently in Denmark. So he's at my old lab and using that at Technical University of Denmark. They're happy to host him. And Farah and Ming Chiang are two students we have a program, International Master of Science in Fire Safety Engineering. That's a program between Lund, Ghent, and University of Edinburgh. So they have also contributed to this work, and of course to the sponsors. If you're interested for more, there's some articles online, just popular pieces, and a couple of journal articles to peruse for those that are interested.
I'm Abhinandan Singh, so I'm pursuing masters here. Yeah. What kind of influence would the angle of the PV panel would have on the flame spread? Like you've decided that this much distance would be a critical distance, so that the flame spread would be lesser. But what kind of influence would angle have?
Yeah, it's a good question. So as you saw in our experiments, we actually opted for just a flat configuration. And again, there are different ways a solar panel some places they are installed in a flat configuration, and then some places they're east-west, and so on and so forth. There are different configurations. The further south you go, closer to, you will have this just flat configuration, whereas in more Nordic or very far south, you will have angles to deal with the sun. But so yes, there are some changes, but we've seen the same things even with smaller angles, and within the angles that are reasonable for installation. So the flat one represents a certain distance. So you can think of it as, if you have an angle, this flat panel will represent some intersection of this. And normally they're installed this way, so it will still be a confinement. So in that sense, you can say that it represents a reasonable selection for that. Yeah.
Any other question?
So more than a question, I am just giving a solution, and I am just asking whether this is a possibility or not. So back 4 months back, we were trying to find out we were trying to extract the parasitic energy from the PV panels. So there is an effect known as Peltier effect, in which the voltage is in brief, if I want to tell about the effect, we can convert voltage into temperature and we can convert it vice versa. So can we use that Peltier tubes underneath the PV solar panels so that we can, in case of a fire break, that temperature can be converted into a voltage, and vice versa, that voltage can be converted into a temperature. However, with this solution, there is a limitation. The limitation is we will need a lot of energy for cooling down. Means like there is a solar panel and a certain amount of energy is coming from there. And that energy that we are transferring to the battery, some part of it will be on the PV panels also. So that is means like we were trying to extract the energy, but in that portion we were losing the energy. But here in this solution, here it can be a good solution because it is just cooling down the panel. There is a PV panel and we are just cooling down it with the help of Peltier tube or Peltier plates.
Well, I think in terms of cooling, I think the amount of energy production from a fire compared to the cooling you could provide, I think would be in favor of the fire still growing, because the panel itself, again, it doesn't have the fire load. It is the physical presence of it that just allows an enclosure where the fire, has a radiation feedback. So if there's a little bit of absorption or not, is not the big thing. One thing you talked about before, one thing that could be considered is to have automatic openings, so the panel actually pneumatically goes open and lets the energy just flow out. But again, that would come at a cost, installation cost, that there's often very small margins for these systems in terms of installation cost.
Okay, thank you, sir.
Okay, let's thank I think we had to stop here. We can discuss during the lunchtime if that's okay with you. Yeah. Let's thank the author for the excellent talk.